Right now, I'd like to introduce the idea of dimension. Why think about dimension? When we're working with a differential equation that's a model for a real phenomena, there might be a large number of different parameters and variables in the equation, and it might be that some of those variables or some of those parameters have the same dimension and some of those have different dimensions. The first thing to know about dimension is that it makes sense to compare two quantities that have the same dimension. For example, I can talk about whether one length is larger or shorter than a different length, or about whether one amount of time, say a minute, is larger or smaller than a different amount of time, say a second. But it doesn't make as much sense to compare a time to a distance. And so identifying the dimension of each of our parameters and variables allows us to see how many different dimensions we have in the problem and which parameters have the same dimension or different dimensions. If we're thinking about constructing our own models, it's important to always construct our equations to have what's called dimensional homogeneity. What that means is that anytime two quantities are added within the differential equation, those two quantities have the same dimension. And actually, even more than having the same dimension, we probably want them to have the same units. What do I mean by that? Well, if one term is a distance and we're adding something else to it, that other thing should also be a distance. But in addition, if the first distance is measured in meters, it would be a good idea to also measure the second distance in meters if we're going to add them together. Once we've identified the dimensions of the various parameters and variables in the equation, we actually will learn how many total dimensions are showing up on our equation. Once we've identified all of the dimensions, it's actually possible to simplify the equations and to identify combinations of parameters that are important. Often an equation has a number of parameters, and it might be a ratio of two parameters that controls whether a bifurcation occurs, rather than a single parameter by itself. I've said a few things about why I think dimension is important, but what is dimension? From a physics perspective, there are some fundamental dimensions. I've listed 4 of them here. Length, denoted capital L when we're just talking about the dimension. Mass, capital M. Time, capital T. And an amount. That could be like a number of cells or a number of molecules. There are a few other dimensions relating to temperature or to electric current, but these 4 are the ones that are going to be relevant for the differential equations that we're working with. As an example, consider the differential equation dA dt equals Ra, and let A be a population of bacteria. So A is the number of cells. When we want to indicate the dimension of a quantity, we use these square brackets. And so I've just said that dA is a number of cells, and so its units are n, a number, because A is an amount. What are the units of dA dt? For a derivative, the units are given by thinking of this as a ratio, a fraction. So it's going to be the units of the top divided by the units of the bottom. The bottom is in units of time, the top is in units of amount. The units are going to be n over t. How do we figure out the units of r? Well, we use that principle of dimensional homogeneity. I could subtract Ra from each side, so dA dt and Ra are 2 terms that could be added or subtracted. They need to have the same dimensions, and that means that the term Ra has the same dimensions as the term dA dt. So the dimensions of r are given by the dimensions of dA dt divided by the dimensions of A, and this is 1 over time. So in this example, we can see that R is actually some kind of time scale. It has units of inverse time.